Up next, we have Guilherme.
Hello,
There.
everybody. Hello.
So you're going to talk about performance. Guilherme is the CTO at Kubos.io. And I'm really actually looking forward to this talk. So the floor is yours.
Nice. Hello, everybody. So this is a talk about performance and how can we use the new I/O ring interface from Linux to get basically a free performance improvement on I/O. This interface it provides a better performance than what we have before, and we can use it without any code changes. So what is this I/O ring? Okay, it's very new on the Linux kernel. It was released on 2019, so it has basically 2 years. But to fully understand it, let's go back a little and see how does I/O work. How can we do I/O on our systems? So we have the Linux kernel, we have our application, and let's say we want to read a file from the hard drive. We send a read system call to the kernel. So we pass the file description, the identifier of the file, a memory buffer, a length, and we send it to the kernel requesting for that particular file. The kernel will pause our application, then try to obtain the file from the hard drive, process it, get response back from the device, and then send it to the application. It will then unpause the application and continue. This is very fast, but it can take, let's say, 5 milliseconds. So it's a lot of CPU time that goes unused. There is a lot of better ways to do it if we need performance. So the most common way is using threads. So this is when we have an application, we start many threads, and now we can use those threads to do I/O. So we send I/O requests from the threads, and now only the threads that are sending I/O will be paused to get it executed. We can have as many threads as you want, doing I/O. We can have another thread not doing I/O, keeping the CPU busy, and this is awesome. And when we get the response, the specific threads are waking up and they start working again. So we can now have an application that isn't blocked by I/O. We can still do work while I/O is being done. We can have many I/O in parallel. This is awesome. But this methodology has a few problems too. First of all, we are using threads. So we have to be very careful about synchronization, coordination, data races. So those threads will need to share state between them, to communicate between them. So we have to use mutex, atomics, some form of synchronizations. And it's very easy to get synchronization wrong. So that's a problem. And also, if we want to scale to doing a lot of I/O, we have to scale to a lot of threads. And now the kernel has to manage all those threads. And this is a lot of precious kernel CPU time being used, and we don't want that. And also, we can't keep up with modern devices. If you have a fast network or an NVMe drive, those are just very fast. And we would need a lot of threads, a lot of wasted CPU, manage them, and we can't keep up. We are basically not using the full capacity of those devices. This is bad. So how can we get even better? How can we improve on that? Then we have evented I/O. This is what Crystal uses, and many other modern languages does evented I/O too. So how does it work? Let's say we want to receive some data from the network. So we have the receive system call to receive data from a socket. And now we are using the non-block option. So sockets by default are non-block, but you can enable or disable it freely. And now that you are sending a receive request with the non-block option, first the kernel will see if there is data on the memory and see if it can reply. If it can't, it will immediately fail with it would block. It means the request will fail. The application get an error saying it would block because the kernel don't have the information really. It has to wait for network, wait for something remote, and doing any of that would block the application. So it will fail immediately, not blocking the application. And now the application knows that that particular socket isn't ready for receiving data. It has to wait on it. And it can use the ePool interface to register this socket or many sockets. And then when the application wants, it can sleep, ask the kernel, please wake me up when you have some information here, when I can read the socket again without blocking. And now on some later time, the information has came, it has arrived, and now the kernel can notify the application, hey, you can try again. You can see this socket here, you can try again because now I have data on my buffer. And the application will send the same request, the same receive request again. And this time it will success because the information will be already on the kernel buffer. This is a little different from using threads, a little more complicated, but has some advantages. First, the application isn't blocked by I/O. Nice, mission accomplished. But also, we are doing parallel I/O on a single thread because we can try to receive it from many sockets, from thousands of sockets. Then we can wait for all of them at the same time. And when at least one of them is ready, the application will wake up and obtain information from it. So we are doing a lot of I/O simultaneously. We can also handle much faster devices with this. So because there is no threads to manage, there is no application to sleep at all the time. It's much more efficient, but has a few problems too. First, we are talking to the kernel a lot. So for a socket operation, we are trying to receiving it, failing, registering, waiting for it, get response, trying again, getting the data. We may need to send more than one system call just to read from one socket or from one file or something. So it requires more system calls than operations. That's a problem. And also, it does not work on regular files. That's a huge problem. Event I/O only works on network. So if I have a file on my file system, or even a networked file system, an NFS or something like that, if it's a file on a directory, it doesn't work. It will simply block. Because you can't wait for when a file is ready. It doesn't make sense. Some applications try to mix event I/O for network and thread for files. It's a mix of both, but that's an issue. So how can we improve from that? How can we go the next step? Now we have I/O ring. And let's now take the time to explain what exactly this is. We have the application, the kernel, and the first step is to create a shared memory between the application and the kernel. This is a region of memory that the application can read and write, and the kernel can read and write at the same time. They don't need to communicate between them to make system calls or anything. They can just write and read from the same memory region. And inside this memory, this shared memory, there is a submission queue and a completion queue. So those are two lock-free ring buffers. It means they are queues. We can insert elements and pop elements at the end, and they are lock-free. So both parties, the application and the kernel, can do operations on the same queue at the same time without synchronization by using atomics. So it's a very specific memory layout, so they can operate without conflicting with each other, given that both the application and the kernel do the exact correct operations all the time inside this memory to not corrupt it. But how can we do I/O with that? First, the application, let's say we want to read a file or send some information on a socket, something like that. It will first describe this operation and insert it to the submission queue. So it will add an entry there specifying the file description, the buffer, the length, the flags, and anything it needs to perform the I/O. So to insert this request to the submission queue. And the interesting thing is that the application inserting this to the submission queue, it's just a memory operation. It's a simple memory operation, nothing else. So it's very, very fast. There's nothing special there. The kernel can then read the submission queue and pop this operation, grab to itself and begin executing. The application can keep sending more and more requests to the submission queue, and the kernel can keep reading and obtaining more and more requests and processing them all at the same time. There is no limit on the number of events being processed in parallel. When something is ready, when, let's say, we requested to receive a data from the network or to read a file, when this operation is ready, the kernel will add an entry to the completion queue, specifying which operation finished and what is the status, if it's completed with success or if it failed, what was the error, and so on. And now the application can read from the completion queue and obtain this completion information and do anything it wants. It will probably correlate with the request it sent and do whatever the application does. And this is all memory operations. This is very, very cheap. For this to work, we have a single system call. I lied before when I said that is just memory. That is a system call, IO ring enter. And what it does is that the application will add requests to the submission queue. And maybe the kernel is aware of this and is reading this memory right now, and it will get this and obtain and pop from the queue. Or maybe the kernel isn't aware of this and is doing something else. So we have to notify the kernel, hey, I have something for you on the submission queue. Please read it. Please take a look at it. And I can do it by filling my submission queue with maybe thousands of requests and notifying the kernel only once. Just to be clear, there is an option on the IO ring to make the kernel keep always looking at the submission queue all the time, so that we don't even need to notify it. It will already know. But by default, the kernel waits for us to notify it. And this same system call can also be used to push the application to sleep until something has completed. So the use case in general is for the application to add a lot of requests to the submission queue. If the kernel didn't read it, then call IO ring enter for the kernel to read it. And if the application doesn't have anything else to do, the completion queue is empty, and the application has done everything it can do. It's now just waiting for this to complete. The application can call IO ring enter to put itself to sleep, waiting for some completion, any completion at all at any of the running events. So this is the layout of it. And it has some nice advantages. First, the application isn't blocked by IO, or that's the usual. We can do a lot of parallel IO from a single thread. So we can submit unlimited requests on the submission queue, and the kernel can keep executing them. So all from a single thread, that is, the kernel will handle it internally. And it can handle much, much faster devices. So it will keep up with any modern device. And this is very nice because we remove the overhead of communication. And it can handle regular files. So it will work for any kind of I/O, network, local file system, remote file system, and even some operations that are not I/O at all, like creating a new directory. It has a I/O ring operation for that. And it can do that with few or sometimes zero system calls. So this is the performance benefits, doing as little system calls as possible. The downsides is that first, it's complicated. So this is a shared memory. It needs precise use of atomics. We can't corrupt this memory, but it's doable. And it's new. It was released on Linux 5.1. And it has been receiving improvements since then. So it has been 2 years just. And I would say it's just ready, starting from Linux 5.6, maybe, is the time when it gets a lot of more features and it's really useful. So it's very new, nice, but we can already use it. And what does everything here has to do with Crystal? So I have been investigating how can we use it on Crystal. Crystal uses evented I/O. So how can we improve on that? And I end up making a contribution. So there is a open pull request in review, adding support for I/O with I/O ring to Crystal. It's a first patch with basic support, so it doesn't support all operations. It's kind of limited, but it's already complete. It does every kind of I/O that Crystal does. So it's not lacking anything, but it doesn't take advantage of performance features. So it could be faster. And I have a second patch that I didn't submit yet to the complete implementation with full performance improvement. As I said, I/O ring isn't supported by all Linuxes. So if you have older installation of Linux, or maybe a not so old installation, you won't have I/O ring. So this pull request, it does a kind of runtime detection. So the executable produced with it, when you run it, it will test if the current kernel has support for I/O ring. If it does, it will use it. If it doesn't, it will try to go back and fall back to the evented I/O. So let's see some numbers. So this is a Crystal conference. I can't go by without showing at least some Crystal code. So here is a Crystal code. It is the first example from the Crystal homepage. So let's see how this simple server can benefit from I/O ring. Doing some tests. This is a synthetic benchmark, a simple benchmark, but seeing how this example can run on a single thread, on a single CPU core, sorry, try to reply as many requests per second as possible. So this is Crystal 1.0. Nice. This is a nice number, about 100,000. This is Crystal 1.1. This is from master, so it will probably get released very soon, but we can see already some improvements. Awesome. And this is Crystal 1.1 with the first patch, the pull request that is open. So you can see that I/O ring already improves quite a lot on performance. And going further, this is the full version with taking advantage of everything. To put it into perspective, here is Go. This is a syntactic benchmark, so I'm not saying Go is lower than Crystal, but we can see how those numbers match each other. And we have Rust. So Rust is very, very good. Neither Go or Rust we use IO ring, so it isn't a fair comparison. And we can see that Rust does a really amazing job. So that is the main point. And also we have the same benchmark running with multiple CPUs, 4 CPUs, using preview M2. So you can see how those numbers match up. I think I'm over time, so thank you.
Right, thank you very much. That was quite a talk. People are pretty shocked in the comments if you see the chat. Someone is saying to shut up and take their money. So I guess someone on Discord will be finding you. You should be having you should have your account ready. So we'll do one quick question. A bunch coming in, guys. You can translate that to Discord. I'm sure Guilherme will be happy to attend there. Jonathan asks if is a plan to use IO Uring for all IO or just files at first?
For all IO. So the implementation really does it for all kinds of IO.
Okay, we can do one more because that was super quick. And Ryan asks, what is the difference between the partial versus the full IO Uring in the graph?
Okay, the partial version, it is using the IO ring interface to listen to events from event IO. So it kind of emulating the old IO interface by using the IO ring. The full version, it's doing IO with IO ring really. So let me try to explain it. The basic version, we use the ring to wait for the readiness event. On the full version, we use IO ring to do the IO, to read or to write to the file.
Okay, great. Thank you so much.